forward to the cloud and there. Can everybody hear me okay? Can anybody hear me?
Yes.
Oh, good. Okay, just checking. Thank you. Thank you. So, welcome to another exciting, oh, shoot. This thing wants to be continued. Okay. Welcome to another exciting class in microcontrollers. I'm going to open the floor to questions. I think there was a question on the floor over here in the classroom on yesterday's lab. Is that right? Did you have a question about yesterday's lab?
It's about submitting lab 2.
Submitting lab 2. Go ahead. What's your question?
I want to show you like what I have, just to make sure like I have everything.
I think it was due yesterday evening, wasn't it? Tonight at midnight? Okay, I stand corrected. All you need to do for the lab is to show a picture of what it is you got working, either in simulation or in the physical classroom. And also, complete code has to be inserted into a Word document. Once you've got the picture and the code in the Word document, upload it to the assignment. I think it's called assignment homework 2 in EE346L. And then you're done. Yes, sir.
I submitted my homework with the code file attached itself without not being on a Word document.
Why can't you put it in the Word document?
I didn't know that I was supposed to.
I think it says so in the instructions. So in the future, please put it in the Word document because it'll render nicely so I can grade the whole thing without having to download a file because it'll just show it on the screen. I'll look at it, give you a grade, and that's it. I don't want to have to keep downloading everything.
I emailed you something.
Well, that's even worse.
No, not the file.
I don't want
emailed you
emails.
The text of the
I
file.
had like over 100 emails this morning. I just can't, I can't deal with it. It's too many.
Okay, well, I'm not sure how to submit again since the homework one disappears.
Yeah, the homework disappears when after the homework is due.
Okay.
So you don't submit after it's due without permission. And then I have to extend it, and then you submit with Blackboard.
Okay.
So if you're trying to submit homeworks after they're due, Blackboard's going to give you a hard time. That's got a computerized deadline in it, and it is not empathetic to whatever issue you may have. Whereas the human being behind the computer is empathetic to whatever issue you may have. So if I put a deadline into Blackboard, it's just a computer. It does what it does, and we do what we do. So we're going to leave Blackboard do what it does. And then if you said to me, I don't like what Blackboard does, we'll change it. So if Blackboard says, oh, sorry, can't submit, it's after the deadline, and you got a problem, and I'm in agreement, then we just change the deadline so that you can submit late. And that's it.
Well,
But don't just email me a bunch of stuff and expect it to get graded, because that's not how I work it. It's just too many people. Too many people. Too many emails, too many things to do. You got any more questions about homework submissions? How about from the Zoom audience? All right. So, yeah, so now AirPlay has decided that it doesn't want to keep broadcasting while I guess AirPlay is just a nuisance. Because it had this working and then it just deactivated. So AirPlay doesn't work. Okay, never mind. AirPlay. Not worth the trouble. You set it up, you get it working, and then it just decides to quit. So there's a homework 3 and a homework 2. Now, remind me, please, did homework 2 come due this evening?
it's due tonight.
Due tonight. Were there any questions about homework 2? All right, then let's move on to the next homework. That's homework 3. Yesterday, we had a question about servos. What can we do to do a servo without doing a resistor for our feedback? And so what I did was I brought in a DC motor with an extraordinary geared down transmission. This came off of an SIR1 robot. And what it has on the back, I'll hold this up to the camera, and you'd be able to see it if we could get AirPlay to work, but we can't. You can see a couple of photo transistors, and you can see gray code has been carved into this metal disc attached to the shaft. So this has got no physical resistor at all. All it does is it measures the rotations of the disc, and that gives you the ability to servo this high gear ratio DC motor, which enables you to get high power, high mechanical power into your servo joint. And I'll pass this around for people to look at so you can see. It's better to pass it around anyway instead of do AirPlay or air whatever, because it doesn't seem to work properly. Unless somebody in the audience would like to try and get AirPlay to work. Would you like to see AirPlay? I have this working, but it doesn't work now, and I don't know why. It just stops.
Do not AirPlay off the iPhone.
Huh?
Just do not AirPlay off the iPhone.
No, not while you're recording Zoom. It's a feature. You can do it off of the device that is participating in the meeting, but you can't do it off of the iPad if it's recording, not at the same time. This is a limitation, which ITS does not recognize. So what I would do today is yes, sir.
You want to just share the screen or?
Whatever you think will work. If you share the screen, will it appear on the monitors in the classroom?
I'm not sure.
Why would that work? I don't know. Okay, whatever. So anyway, we're going to do duplex.
Professor,
Yes, sir.
there's a question on the homework. Ugo has a question in the chat.
Okay, I can't look at the chats while I'm teaching. Can somebody tell me what it says?
Yeah, he said question 19 of homework 2.
Okay, and I don't have homework 2 in front of me. What does that say?
I'll have to check. I don't have it in front of me either.
All right, well, I can't seem to get the AirPlay to work. When someone can find it, let me know. So today we're going to do duplex. We're going to do SPI programming. We're going to talk about the signals, MOSI, MISO, and serial select. We're going to talk about some of the, I'll call it macro directives inside of the C component.
T'en veux? Il y en a dans la boîte.
I beg your pardon? Oh, we got it.
Good morning.
All right, so here's what it looks like. Is this what you're asking about?
Yeah.
Okay. So the question reads, consider the following setup. How would you write a for loop for the LEDs from left to right? We already discussed this in the last class. I think you can watch the recording from the last class and get an answer on this. It does seem to have an answer, and people seem to agree. You need to write, well, there is a solution that uses a for loop and runs from pin 2 to pin 8, going from right to left if you hold it one way, and left to right if you hold it the other. So it all depends which side up you use. And then someone else says equals to less than 8. Is that wrong? Equals to less than 8. No, that actually is a solution. So it runs from 2 until you get to 7, I guess. I can't see what the pin is because it's too small, but that's all I can see. Can you see which pins it works to? So, yeah, I think there is a solution. Is that pin 7? I can't see it.
Yeah, 7, 6, 5, 4, 3, 2.
Yeah, so we're correct. It goes from pin 7, 6, 5, 4, 3, 2. And then if you start on pin 2 and work up to pin 8, but not including pin 8, that's why there's a less than, then it will reach pin 7. And that is a correct answer for question 19. Thank you. Are there other questions about homework 2?
Is your device hosting the meeting?
No,
Or is it that?
this device is hosting the meeting. I just wanted to be able to do AirPlay.
Well, everybody's
Oh, good. Yeah, it's working now. I see that.
But one issue is I don't know how to pin the video for this one to be the main.
Yeah, I don't either. I don't think it can be done. It's a feature. Oh, it turned itself off.
No, it's because someone else, when they speak,
Oh,
they pop up on it.
I see. All right, so unless there's more people, I guess you guys should mute yourselves. Or I'll mute you. I don't know if I can. I'm not quite sure how. But anyway, under participants, maybe? Ask all to mute, mute all, mute all, mute all. There, I think that worked. Okay, so everybody's muted now. If you want to talk, you're going to have to unmute. So, homework 3, which is going to be due on the 24th, end of day, contains 14 pages and 31 questions, I think. Yep, 31 questions. And what we're going to do is we're going to discuss topics of duplex serial programmer interface, MOSI, MISO, SSI, and macros. I wrote macro directives. In macro directives, what we have is a C preprocessor, which is invoked for both C and C++, and Arduinos are being programmed in C++. Therefore, the macro preprocessor is going to be running before the compiler, or if you like, as a part of a macro preprocessing pass. So this is being run as what we shall call a pre-process. Pre-process. What that means to you is that you will not be seeing compiler syntax errors, but macro syntax errors when these things go wrong. Moreover, what they can do is they can do direct substitutions, and they can do includes. Here's the typical include directive. # include. # include can take an absolute file name. That is to say, if you have something like C:\lion /programs / the stuff I want to include .h, you can put that whole thing right after include, and you can put it in quotes. And that is going to be an absolute path name, APM. I'm going to abbreviate it. An absolute path name. And unlike every other C statement that you will have encountered, it does not have to be followed by a semicolon. That is one form of the include. Sometimes you will see something like this. # include quote, DAC .h. Case matters, like in real file names for your file system. So if you get the case wrong, it'll be a file not found at compile time, or at pre-process time, if you like. Another form might be something like this: # include, quote, adc.h, end quote.
What's that library?
That's the analog to digital converter library. The other one is a DAC library. These files can be geographically co-located in the same directory as your main code. So what that means is the compiler will automatically look there. There are other places it can look depending upon what the path is as it's been set for the compiler, the so-called include path. If you use a variant of the include, and we're going to discover these things are available to us whenever we start using examples from the Arduino library. One of the variants will be include angle bracket SPI.h, and angle bracket. That angle bracket is special. What that means is it's part of the system library. So that might be some sort of a global library for which you have installed some, we'll call it library objects. Library objects are interesting. They're typically in some sort of a file called lib.o. This is relocatable compiled code meant for the Arduino. This is Arduino binary code. It is going to be included as part of what is called a static linking process. And so what this does is it allows me to describe for you in brief the process. We start with source code. And the source code goes into the macro preprocessor. Right? And that's going to work with these things. SPI.h is going to have a series of declarations. Those declarations will describe what's contained inside of lib.0, the object file. Then you're going to have your main C program. The main C program will be modified by the macro preprocessor to include all the declarations that are in SPI.h or in any of the includes that you may have included, including things that are not libraries. You could include a whole extra program if you want. In fact, that extra program could include other extra programs. And then you can nest the includes, and that will cause compile time to slow, that you can just keep going with nested includes, going and going and going, 10, 20 deep, until things just don't work anymore. And then what happens is you go into the C compiler, the C++ compiler, and then what comes out is an object program. The binary object program has now been generated and can be stored locally to a temp disk. In the Arduino, preprocessor, compile, and linking is done in this phase. So linking means we're going to insert through the linker the lib.out. So now lib.out and a.out and your main.c are all sort of related through this C compiler, which actually introduces a linker. Then you have a communication path which goes to the Arduino, and you can change what that is, but somehow the a.out gets downloaded into the microcontroller. And then the microcontroller starts to execute the a.out. That's the basic flow. Compile, link, and load. So here's the sort of compile stage with the linking built in and then loading into the microcontroller. Compile, link, and load is a programmer loop. That programmer loop is a loop that involves a human being. That human being is you, the programmer. When you make a change to your code, you've got to compile, link, and load. Test the code, see if it works, then go back and do it again. If compile, link, and load takes a really long time, that is going to harm your productivity as a programmer, because you're going to make one tiny little change, you're going to do, and it's going to go, you forgot a semicolon. Then you got to go put the semicolon in and go, and then it goes, this is not a defined constant. And then you're going to go make a defined constant, and you're going to go, whoop, and it's going to go, and you're going to say, oh, every time you type, the computer goes, and then you're going to learn that you have to actually read the code and think about it before you get involved with the compile, link, and load, because it takes so long. And in fact, everything we've done so far has been a program that runs less than 20 lines of code. Believe me when I tell you, once you get involved with real industrial code, it's not 20-line programs, and it's not 200-line programs, it's 200,000 or 2 million line programs, and compile, link, and load takes a really long time. So long that people will be running it overnight, and then coming in the next day to see what went bleh. And then you have to really think about what it is you're doing before you start typing the code and submitting it to your version control system. But for us, it's okay. We're trying to run one little tiny sensor or one little tiny actuator, and then it runs really fast and it's fine. So we don't have to care about that, at least not too much yet. I've been involved where there were macro directives nested 10 deep, and including files left and right. And you'd include a file which included 10 other files. And it would just go on and on like that, and it was so hard to debug. So difficult. So those are the macro directives that we've seen so far. This is what we've seen in the lab. We actually used, I think, something that looked like this, only it was for servo.h. So what's in the servo.h file? Well, the answer is it's a declaration of all of the subroutines and what they take. So what they return, functions that return values of different type, and also the arguments, the parameter list that the subroutines take. So what did I learn? If it has an angle bracket, it's a system include. That's what I learned. If it has single quotes, it's probably a file that's geographically co-located with my main program. Or if it has an absolute file name, absolute path name, then it's probably something we can find on the C drive somewhere or on the Mac drive. Mac drive, it's not going to be C:, it'll probably be \, I don't know, home \, lion \, something else. Let's see now. That covers the basics. There may be other things that we'll encounter. For example, there is a special method called setup. Okay. That gets run once and only once, returns void. And change my marker a little bit, see if it gets even darker. And so with setup, what we'll do is we'll do something where we initialize, such as that in there. And that will initialize the DAC, and we'll call it once and only once. And it may take a while to initialize the DAC, but that's okay because we only need to call it once, and it just delays our startup a little bit. And things have to be initialized. We don't have any choices in the matter. We might like to communicate with that DAC, and if you have the audio shield, it's an SPI DAC, and SPI stands for Serial Programmer Interface. And that is a common high-speed serial interface for our little Arduinos to communicate with a wide variety of different devices. So far what I've done is I've covered enough material for you to do homework 3, problems 1, 2, 3, let's see, 4, all the way through 6. Here's another aspect to the basic Arduino. that we are using, or we call it the Arduino Uno. In Arduino Uno land, you have a finite amount of memory. That finite amount of memory impacts what it is you can do as a programmer in ways that are really different than if you were on a desktop computer. For example, on a desktop computer, you can have a constant. N equals 1500. And then we can have a byte array, data array N. And what this does is it declares an array, a byte, that's 1500 bytes long. For the Arduino, can we make N any number we like? Any ideas? What if I wanted to make N 15 million? Does that make sense for the Arduino? What if I wanted to make it 15 gigabytes? Would that be okay? I mean, C doesn't stop me from doing it, does it? And the answer is no. C will let you make this number anything you want. It's not a compile time error. But it isn't going to work. Why? Because it's a little tiny 8-bit toaster controller, that's why. It's got 2K of RAM. You try and go beyond 1500 bytes, and you're not going to have enough room to breathe. 2K of RAM is like 2048, and there's going to be room for scratch memory, too. So after 1500 bytes, you're done. That's it. Arduino's finished. So this is an Arduino problem, right? This is not a C problem, but it is a practical problem. When you have finite hardware, you can't just keep going. And that is the answer to question number 1 in homework number 3. So now we've gotten through homeworks questions 1 through 6. That's pretty good. Any questions so far? Suppose I wanted to communicate with a device. And that device, let's say it's the DAC in my case, the DAC on our shield. How do I do that? How do I communicate to it? And the answer is we use the serial programmer interface. And a serial programmer interface is a synchronous serial interface. Synchronous serial interface means you're going to have, in this case, a master and a slave. The master is going to have a serial clock. This is what makes this synchronous. Right? And there's going to be a serial clock input on the slave. You want to do fast communications to something like a digital to analog converter, you might as well make it synchronous, right? Because you're going to be outputting data really fast. Then you have a master output, slave input, which we call MOSI. And then we have a master input, slave output, which we call MISO. Like the soup, like miso soup. And to select the slave, we have a select called not SPI select. And that's an input here. And that is the wiring diagram for one device. Let's have a short interlude and talk about the idea of duplex. So we talked about SPI, MOSI, MISO, serial select. What about duplex? What does that mean? What's duplex mean? I have duplex communications with the people in this classroom. No, that's close. It's not direct. Duplex. Here, I'll give you an example of back and forth, two-way communications. So two-way equals duplex. What about this other term I'm going to use, simplex? That's one way. Let me give you an example of simplex radio communications. Let's see, Bridgeport Tower, Archer November 4329 Papa requesting touch and go. You let go of the mic, what happens? It says, 29 Papa cleared for touch and go. And you respond, 29 Papa cleared for touch and go, and you go and you can touch and go on the runway. And that's one-way communication. What happens when two people or more people try and talk at the same time is you get a feedback tone that lets everybody know they stepped on each other's communication. Only one can turn to talk at the same time because it's a big party line. And it's all being shared by all the crazy loons who are flying around the airport. Big jets work this way too. They have to respect each other's communications. Yes.
So a phone call would be duplex.
Phone calls are duplex because you can talk at the same time. But if you get on the ham radio, it's WN2YIF over, and over means you're done, and it's over to you. And now you can talk. So we take turns. That's simplex. Simplex means taking turns. Duplex means you can talk in both directions at the same time. How come it's duplex? Because I have a master in from the slave out. So I can communicate to the slave, and at the same exact time, it can acknowledge. Moreover, when it does its acknowledgement, the bit framing will be dictated by the serial clock that comes from the master. What does that mean, bit framing? I don't understand. Can somebody please explain the term bit framing?
Zero translated into bits.
Well, there's bits going back and forth, no doubt. But what we want to know, 0110111, is when the 0 begins and when the 1 ends. How do I know that this is 3 bits? And the answer has to be because of timing. So if I have sample timing, right, from a regular interval clock, then I can know when to sample the input, when to measure the voltage, and figure out what the value is. This is a form of modulation known as baseband modulation. It's the simplest form of modulation, baseband modulation. The signal either appears or it does not. Smoke signals are an example of baseband modulation. They are also, able to travel at the speed of light. Wow, smoke signals. But the data rate is really small, or low, because you can't really make smoke signals happen quickly, I think. Although, we could make that a senior project. So, yeah, smoke signals, I like it. So there's a compelling argument that smoke signals operate at the speed of light. Are smoke signals synchronous or asynchronous? They're asynchronous, right? Because there's no separate serial clock coming through. So they have to have their own clocking mechanism, which means you have to have some way to discern the difference between a long puff and a short puff. And then you have to separate the puffs. I'm not real good with smoke signals. I've never actually tried that.
Can you tell us what SPI was again?
That's the Serial Programmer Interface, SPI. So SPI is a baseband duplex synchronous serial communication. Isn't that interesting? So it's baseband duplex synchronous high speed communication path. That's what SPI offers. Moreover, it's built into many chips that we can buy commercially and plug in to our Arduinos. And we have libraries that support SPI programming, which means that we can make use of these chips with relative ease. We still need to know how to operate the underlying hardware. We have to know if it's a 10-bit DAC, how fast it goes, what kind of serial clocks we can use, various interesting and wonderful things like how you order the bits in order to get them to come in, whether they come in 1 byte at a time or all 10 bytes, if they're all 10 bits, if it's a 10-bit DAC, things like this. But in other ways, it's very standardized. So this is what you call physical layer. Right? So this is a baseband duplex synchronous high-speed communication physical layer. But if there's more than that, it's 1 layer bigger. It is also in the data link layer. The data link layer does packets, moving packets from one point to another. So link access protocol allows us to detect small errors in the transmission. These might be something like parity errors. So we have an opportunity to essentially recover from small errors, but not big ones. And there's an opportunity for us to exploit this for commodity commercialized devices that we can attach to our computers.
Professor,
Yes, sir.
would you mind reiterating how you can tell by like looking at a configuration, whether it's simplex or duplex?
Sure. In this particular case, we know it's duplex because we've got an output from this master and we've got an input from the slave, and they can both communicate at the same time. To give you an example of a simplex communication path, consider, for example, Voyager, the satellite. It's actually beyond the heliosphere. At that distance, it cannot see the Earth. However, it is possible using the deep space network with an array of satellite dishes to beam data to the Voyager satellite, but it has no way to answer. So that's one-way communication. When it comes to ham radio, it's one way at a time. You have to take turns. So that's the difference between duplex and simplex. When you think about the telephone, we can both talk at the same time. So the telephone gives us a full duplex communication path. Sometimes having 2 people talk at once is rude, and they interrupt each other. And I've seen this happen a lot. I don't particularly care for it, but it's become almost normal. Then comes another problem. I really like this. This works great. But what if I want more than 1 chip using this SPI bus? What do? I got another chip. I just bought it at the store, the chip store. I think they sell them on Amazon, actually. So let's assume this is, 1 DAC. Here comes DAC number 1. And now I want to have DAC number 2, because why? Because I like stereo, and stereo needs 2. I don't know, for no reason. DAC 2. Here comes DAC number 2. DAC number 2 has the serial clock, MOSI. Well, I'm going to write larger so you guys can see it. Serial clock, MOSI, MISO, and serial select. And the serial clock that this device uses is going to be the same as the serial clock that this device uses. And the MOSI that it uses will be the same MOSI that this uses. And the MISO will be the same MISO that this uses. How do I differentiate? I'm just going to wire OR. There. How do I select DAC number 2 when it's time to output to the other DAC? And I could do that often, right? I could say, okay, DAC 1, here's a sample. DAC 2, here's a sample. And the two samples are different. One's for the left channel, one's for the right channel. I'm building a stereo, right? How do I choose which DAC I'm outputting to? Any ideas in the classroom? Any ideas in the Zoom audience? Hi, Zoom audience. Any ideas? Yes, sir.
Use an encoder or decoder?
Yeah, use a decoder, right? So if I have a decoder, then what I'll do is, and I don't even need a decoder, right? Because I've got an Arduino and it's got a bunch of I/O ports. So if my I/O ports are available, I can use my I/O ports. I can use pin 9 and pin 8 on my Arduino, and I can make it so that pin 9 chooses this device and pin 8 chooses that device. And if I put a decoder in there, a 2 to 4 decoder, I can have 4 devices, but then I need a chip. I don't want to add another chip because it makes my cost increase. But maybe I could. I mean, if I had 3 bits, I could have a 3 to 8 decoder. And then the 3 to 8 decoder would let me directly address 8 different devices. But they have to take turns. I can't address them all at the same time because they're sharing a bus. And when they're not selected, they have to drive their outputs into a high impedance state. And they have to ignore the inputs. Have to ignore them, except for maybe the serial clock. And the reason is, you know, if you don't, then what's going to happen is you're going to start outputting spurious data on one of the DACs. And then it isn't going to work right. So in comparison to the servo used a baseband modulation technique called pulse width modulation for adjusting its angle. Here, we're actually using digital data communications, using a baseband duplex synchronous high-speed communication physical layer in order to be able to do our communications to the various chips that we're going to add to our little Arduino. And that is an example of our first bus, right? Because when you start to wire different devices to the same wires like this and then select which device you're using, that makes it into a bus. And busing requires a tri-state logic system. That is, busing requires that you be able to take a device and put it into a high impedance state so it does not assert the lines. Because if 2 devices assert the lines at the same time, one device can say you're a 0, and the other device can say, no, you're a 1. And then it's the moral equivalent of a short circuit, because a 1's going to be 5 volts and a 0 is going to be ground. And if you put 5 volts to ground, your transistors will get hot and unhappy, and it will blow out in milliseconds. And now you have the answers to questions 9 and 10 in homework number 3. In this case, when you have to take turns, is it simplex or duplex? Are we able to, have we defeated the duplex communications? And that's a tricky question to answer, I think, because the answer is, yeah, you have duplex, but it's selective duplex, and everybody has to take turns. And taking turns is the essence of enabling what I would call a simplex-only communication path. You can't have this turn into a party line where all of the devices talk at the same time. When there's just one device, sure, it's full duplex. But when there's multiple devices, even though they're the same exact device type, you've created a simplex system where things have to take turns. And that's important to notice, right? So what has happened is the configuration enables simplex-only communication. And you can tell, you ask, how do you tell by inspection? This is how you tell. If I can't have this device talk at the same time as that device, and you're taking turns, it's really a simplex system. It's not a party line. What would be an example of a party line? Any ideas? This is a basic digital data communication systems question. So how about Ethernet? With Ethernet, you have many entities dropping packets at the same time into a shared system. Now, if they actually do at exactly the same time, instead of taking turns by time division multiplexing the packets, you have what you call a collision. And the technical name for Ethernet is CSMA CD. That's carrier sense with multiple access and collision detection. Yes, everything can talk kind of at the same time, but what you do is you develop a time division multiplex system, and when two devices try to talk at the same time on the same local area network, the collision is detected because they sense the carrier. But they do permit multiple access using time division. So in a sense, one can claim that it's like a highway. You can drive on the same highway as everybody else, but you've got to be careful when you merge in. You don't just merge in without looking. You merge in after you've been given permission or after you're sure it's clear and safe, and then you merge in and you can get in off the on-ramp and merge with the traffic. But you don't just pull in front of people like happened to me today. That's not nice. Causes collision. And when there's collision in the real world, bad things happen. It's not just going to try and retransmit at some random time, because then you have to go and deal with insurance companies. So it's an interesting sort of analogy. Any questions about SPI? I'm just going to quickly go through this and make sure there's no more SPI questions here now that we've gotten everything sort of squared away with SPI. I think we got everything. That's all we have for SPI on homework number 3. And SPI programming is it's an important form of programming when we want to get involved with programming the little serial DAC on our audio board, because that's how it works. It works via SPI. Very practical, very high speed, nice way to communicate. And Arduinos are all over it. You can buy tons and tons of shields that use SPI communication. In fact, I think, me personally, the reason why Arduino continues to be the superior way to do this kind of microelectronics is because of the Arduino ecosystem. Arduino ecosystem consists of many, many people making compatible devices. Today, I think it was Chris Lafke who sent me an email who said, oh, I found micro megas for 99 cents on eBay. And I said, holy crap, look at that. And the price was right, but they were charging $3 for shipping, but I didn't care because it was a mega. And it was just like an Arduino, only they had packaged it in this really tiny printed circuit board. And I'm like, how can these guys afford to make these things so cheap? It's almost as though they're exporting their unemployment by subsidizing manufacturing, which would be an unfair trade practice. And I wouldn't want to accuse anybody of that. So that's, I mean, this is part of the Arduino ecosystem. Arduino Mega is like an Arduino Uno, only with lots of extra I/O and with more RAM and more ROM, and all these other things attached, and faster, and 32-bit or 16-bit, depending on what you get. So it's kind of interesting. Get beyond the 8-bit toaster controllers with these things. That's a compelling argument, right? Because people say, oh, I like Raspberry Pi because X, Y, Z. And I think Raspberry Pi is a great computer, but it requires an operating system. And what we're doing here with what it is we're able to create is whole new hardware systems that we essentially can integrate to create new emergent technologies that didn't exist before. People aren't doing a lot of, well, they're not doing the same hardware hacking with the Raspberry Pi that they're able to do with things like Arduino Uno. Let's see now. So that's what I've got for SPI. We did a little duplex. We did some discussion of simplex. We talked about digital data communications, macro directives, preprocessors. Here's a for loop. For bit equals 0x80, semicolon bit, semicolon bit greater than equal 1. This is sort of C puzzle code. What's that do? What does greater than equal 1 mean? What does that do? Well, this is going to do a bit equals bit shift 1. That's what that does. And when will it stop? Yes, sir.
Or stop after 8 times the 0.
Yeah, okay, what is 80? This is a hexadecimal number, right? So that's going to be 1 0 0 0 0 0 0 0. So there's a hex number 0. Here's hex number 8. I'll put the X in front of it. So now it's 1 2 3 4 5 6 7, and then on the 8th bit it'll be 0. Once the bit value is 0, I should say bit. I should say bit. And this should say bit as well. Once the bit value is 0, it will stop. So it's going to keep running. It's not using a Boolean object in the argument. This is like a while loop without a Boolean. Instead, it's using a scalar value and treating it as though it's a Boolean. And when it's equal to 0, it's going to treat it as false. So this will continue to run until bit is of value 0. It'll treat it as false, and then the for loop will stop. That's what that does. It's not the kind of code I like to see, but I have seen it in many of the examples, and when you encounter it, you're going to want to know what it means. And so this is why that's it. I don't recommend coding this way, but I've seen it.
Why don't you recommend that?
Because this over here is a C idiom, which basically is equivalent to that. And that is much more clear to me, and I prefer clear code. So, I mean, you can say be greater than equal 1, and that saves you typing. But if you said b equals b greater than 1, it doesn't take that much more characters or that much more space, but it adds a whole bunch more clarity. It says you're shifting b over to the right once and then resetting b.
I'm pretty sure you could put that in the for loop itself.
Yeah, you can.
Yeah.
You can do either.
Yeah.
Either will work, but the question isn't what will work. The question is, what do you prefer in terms of your coding style? I have a preference. My preference is clarity is better if you can achieve it. And so that's why I prefer something like this. It's my preference, okay? You know, you can establish your own code style. And if you use somebody else's code style, I'm not going to take grades off, okay? I won't take off points, but I'm telling you my preference. So that's that. And that, oh, by the way, this is the answer to question 13 on homework number 3. So we're getting there. I mean, it's taking us a little while to work through it. Part of what we're doing is we're learning a kind of C and C++, and even Java will do this too. Java, by the way, everything we've done here, Java can do. And C# even. C# will accept a syntax like this. Problem is, we're trying to deal with low-level bit manipulations because a lot of the devices we encounter have to be written to at the bit level because you're writing your own device driver. And so that's a critical problem that you're going to face when you start to do hardware-based programming. This is what you might call systems programming. Right? Because what you're really trying to do with the bit flipping is you're trying to get deep into the understanding of the hardware. Let me tell you something. When I did this sort of thing for a living, I ended up poking my nose into the data book for all the chips that I was using. And I had to do the same thing for the microchip DAC, right? If you don't read the data book, you're not going to know how to flip the bits and you're not going to get it to work. It's as simple as that. So a lot of times there's no programmer guide, there's a data book. Read the data sheet on the device, and then you can learn how to program it. And so a lot of times they don't even care that you're using an Arduino. In fact, they don't want you to use the Arduino, they want you to use their products. The microchip products are not the same products as Atmel products. Atmel products, that's the 328P, that's your Arduino Uno. We haven't talked a little bit about the chips inside of your computer. They come from Atmel, a semiconductor manufacturer. Microchip makes a DAC. They want you to use the PIC. The PIC microcontroller is a microchip microcontroller. They don't want you to use Atmel. They're not going to cater to Atmel, but they'll give you a data sheet, and if you want to use their device on the Atmel processor, you got to figure it out. And that means you got to read the data sheet. It's not that hard. Nothing's that hard. But it ain't simple and it isn't easy. So it's just a lot, there's just a lot to learn, a lot of things to deal with. You know, anybody can program badly, but if you want to do it well, it takes work. It takes work. So let's assume that I have a device and I want to define it as my DAC. That's my digital to analog converter. And I'll give it a pin number. Let's call it DAC1. And I'll do something for a pot, my potentiometer. And I'll define the pot. And I'll call it pot 0. Notice there's no semicolons here. What have I done? What is this? First of all, look at these hash marks. These hash marks represent compiler preprocessor directives. These are macros. This is not going into the compiler directly. This goes into the preprocessor. Everywhere it sees the term pot, it's going to substitute the literal 0. And it's not going to care if pot is supposed to be a string, or if pot's supposed to be an array, or if pot is supposed to be something else. Unless it's quoted in strings, in quotes, it's going to go and find the pot and do the substitution. So it's not going to cost you any extra storage in terms of another variable. It'll be a literal embedded in the code. And then the C compiler will find it. Here's what you might have done when you had include. I'm writing it too high. Just a minute. Pound include angle bracket DAC.h. That is a system include because of the angle brackets. Once you did that, what happened? You got a bunch of other macros, right? Somebody defined DAC to be of type 1, pot, not type 1, but the value 1, pot to be a value 0, all inside of the DAC system. Maybe there's something called chip select, and there's a standard pin for the chip select. Define chip select. And this would be the same thing as the serial select for the SPI interface. You need a pin. So pin 9, all in DAC.h. And that's what you get when you try to use the SPI DAC, the counting with your sound output device. And most importantly, void DAC right unsigned integer, UINT, 16 underbar T, 16-bit unsigned integer, semicolon. I haven't told you how this was implemented. All I did was I said when you include DAC.h, this declaration will appear in your code, which means the compiler can use this provided that the linker gives you the binary that it can link to. So it doesn't give you the source code. What it does is it gives you the prototype that you need in order to be able to invoke the subroutine. There's also another one called void DAC init. And so what you can do once you include a subroutine library like this, and you have to know how to use subroutine libraries. There's just no way around it. If you're going to program microcontrollers, you've got to know how to do this. You're going to have a setup which does a DAC init. That'll initialize the DAC. Then you're going to call DAC write repeatedly, and then you're going to write out data to the DAC on your sound card. So where is the chip select? This is the question known as question 14, homework number 3. Where is the chip select in this code?
Pin 9.
Yes, pin 9. It's clear, right? And that is where you have to wire the DAC. If you were to overwrite the chip select and change it, you have to change where the DAC is wired. But if you have a printed circuit board with a pre-wired DAC, you don't have that option unless you want to go in and get a little knife and cut the wire and then, I don't know, solder something to a different pin, which you could do. You could do that. Or you could get a DAC of your own and you could put it on a breadboard and then wire it to wherever you want. Not that hard to find these DACs. In fact, I have spares if you guys want to wire DACs up. What do you think so far? Are people sort of following along here? This is different, right, than the kind of coding you might have done when you were Java programmers, because you've got to do this compile, link, load thing. And you have to define the prototypes for using the subroutines before they appear in your code. Or else the compiler is going to look at that stuff and it's going to say, I don't know how to do a DAC right. How does that work? I don't know how to do a DAC init. I don't know how to do those things. But if you have it in the prototype, the compiler will say, oh, there's some sort of a subroutine I can link to, and I'm going to find the symbology for that in my linker, and it'll give me an address. I'll do a subroutine, a jump to subroutine. And this is not just my DAC. Right? This is anybody who has anything to do with any subroutine library. You're going to need to have prototypes for all the subroutines that are in the object code, because they're not giving you the source. They're only giving you the object code, and that might have been written in assembly for all you know. CBI. CBI is a macro preprocessor directive that is the moral equivalent of a function invocation that happens before the compiler even gets invoked. And what that does is it clears a bit. And there's another one called SPI. And that sets a bit. Set bit I. And these two are used to set and clear individual bits. Here's a kind of programming which I really dislike, I call it, for no particular good reason other than that's what it is, I call it bit flipping. This kind of directive is meant specifically to simplify the bit flipping. You have to do it. I don't care to do it, but I have to do it. Why? Because that's what it's like to write device drivers for little chips that you add onto these microcontrollers. You've got to do some bit flipping. So having some macro directives that allow you to set different bits is convenient. CBI, let's see now. We'll have a register here called the shift register, SFR. And what I want to do is I want to clear bit 1. So I call CBI SFR1. And I do it without a semicolon because it is a macro directive. It gets invoked directly and it will essentially clear a bit. You can do SPI, SFR, 1, and that's going to set bit 1. So CBI and SPI will allow you to flip bits either on or off. So that's kind of convenient. And that's the answer to question 15. How am I doing on time? Oh, good. I still have some time. That's good. Very good. Any questions so far? I'm running you through these basics on programming because you probably haven't seen this before. And I'm going to guess that it's a little bit different than the kind of programming you're used to. And as we get deeper and deeper into the programming of the Arduino, we're going to find out that there are a lot of these sort of little subtleties that we have to deal with. Here's another macro. So far, we've discussed really basic macros, and we haven't really talked about how to do macro programming. Macro programming is practically its own language, a language in and of itself. And what we're going to do is we're going to define bit vector as equal to something that takes a bit, type in, and shifts it over. I make a little room for myself up here. Another parenthesis. Yeah. So what does this do? This says I want something that's 8 bits long. This is going to take a 1 and shift it over by 8. So if you call integer I equal underbar BV of 8, what that does is it makes I equal to 1, 1, 2, 3, 4, 5, 6, 7, 8 in binary. That's the equivalent. And this is going to happen in the macro preprocessor, so it's not going to take any more CPU time. The macro preprocessor will run the shift. And it'll do it and embed the literal right in through here so that you can have the value assigned. So that's a bit vector that is a 1 followed by a bit number of zeros. In this case, 8 zeros. So that's a slightly different use of define. Before we saw define was used as includes. Then we saw define was being used Well, perhaps just a substitute. Now we see define as kind of being used as a function. And we didn't see that before. And the macro preprocessor can execute these functions. It has its own little programming system built in. And that's the answer, by the way, to question 16. How am I doing so far, guys? Everybody sort of understanding what we're doing? So macros, how many people have seen macro programming before? Anybody out there? I'm gonna look at the participants' hands here. Anyone showing a hand? No hands? Yeah, so this is new. This is new stuff for everybody, I think, right? Pretty new. And so it's not easy, and it isn't particularly simple. There's a way to declare constants. I think you can do this in Java as well. You can declare integer I equals 0 as volatile. It's A. V-O-L-A-T-I-L-E. Volatile. V-O-L-A-T-I-L-E. Volatile. When you declare a variable as volatile, you are giving the compiler a directive that says you can optimize the compiler because the values can be changed by code outside of the scope of the current code at any time. So volatile code, maybe it gets changed because it's in the address space of a register that can do direct memory access to your CPU. And that is an interesting concept. A lot of times what will happen is RAM has devices that reside at a specific address. And what will happen at that address, let's say it's 0200, is the ADD converter can write to that location some value for the CPU to look at later. If that value comes in and gets changed without the compiler and the runtime knowing about it, then essentially what's happening is the analog to digital converter is being invoked as a side effect. It's changing because it's actually able to get new data in, and it memory maps that data. And what you want to do is just read the value at that memory location, and the analog to digital converter will handle all of the details of getting that data into that memory location. So declaring the object as volatile is useful for you as a programmer because it lets the compiler know to expect this data to change and not cache it, not store it someplace in the CPU in a register and say, no, no, we know that data, we don't have to go get it again. What it says is, yeah, you better go get that every time you make reference to it. And then comes pointers. Now, pointers is a really big topic, and it's kind of hard to get into, and we're out of time. We're up to page 9 of my system here, and we're out to page 18. I think that's all we have time for today. Let me just check. Yeah, we end at 12:15. So that's it for now. But what I'd like you to do is take a look at homework number 3. See if you can't get through the book and learn a little bit about pointers. It's an interesting topic, and I think you guys will learn a lot from it. It's probably not something you've seen before. So thanks a bunch, and stay safe.
Thank you.
Thank you.